So our second lecture is a bit of an introduction to hardware modeling with hardware description languages. Not necessarily all about VHDL. It applies to hardware description languages in general, just to give you a flavor of what hardware description languages are all about. So what are basically our goals? Of course, for this module, as I said in our previous lecture, what we want to do is essentially to learn VHDL. Yes, you can. No, you don't need to fill the registration form again. So the idea, of course, is that hardware description language like VHDL can basically model digital systems at different levels of abstraction. And it can deal with extremely complex designs as well. But any hardware description language essentially has a subset of instructions which can be used to synthesize stuff. So essentially to run that code on hardware. But there are also some instructions which cannot be used for synthesis purposes. So their job basically is to assist, for example, with simulation or with other aspects of the environment. We would primarily want to learn those type of instructions in VHDL, which can be synthesized, because of course those are then practically useful in order to create designs. We also want to learn the tools which support VHDL simulation and synthesis. And as I said earlier, that would be the VHDL, the software from Xilinx ISE version 10. We also want to introduce you basically to ASIC and designing with FPGAs and CPLDs as well as part of this module. So those are our some of our key goals. First things first, let's try to understand what a hardware description language is all about. In short, HDL. That stands for hardware description language, as you can see. Essentially, a hardware description language is pretty much like a high-level programming language. But the difference there is that this type of language is basically used to model hardware. So any sort of instruction in VHDL ultimately maps to a hardware resource located inside of a CPLD or FPGA device. Hardware description languages, unlike languages like C, for example, have some very special hardware-related constructs and behave in a very special way as well. Currently, hardware description languages are really meant to assist with designing digital systems. In the future, they might well be extended to modeling analog systems as well. But for the time being, they are all about creating digital designs. What they are also very good at, and this is part of the whole idea of creating complex designs in quick time, they can basically perform simulation quite extensively to make sure that our designs behave exactly as intended. And then once we are satisfied that our designs work as intended, we can then proceed to the synthesis process, which actually generates the programming file that configures a CPLD or FPGA device to essentially behave in the way the program tells it to behave to create that particular design. These hardware description languages are very, very good at a number of things, including designing very large system-level designs, and including dealing with modularity and designs which are very complex, hierarchical designs, that sort of thing. They are basically, or they have been designed to work quite seamlessly that way, which is very useful indeed. What makes HDLs different compared to other high-level languages is the fact that they basically are concurrent in nature. What that means is essentially what I said earlier on in terms of the concurrent nature of hardware. In hardware, we have basically ultimately transistors deep down inside of any digital device, and those basically run by pretty much having electrons flowing into them with the speed of light. So everything is concurrent. It happens all in parallel. To capture that sort of concurrent nature, that's why we need basically to have VHDL or hardware design, hardware languages in particular. They tend to be distributed in nature as well, and that is also quite handy. Because essentially, when creating larger designs, it is quite often the case that we might have a lot of different components in there, and those could be all modular, and they could then be all put together hierarchically using these hardware description languages. As I said earlier, HDLs are very, very good at that sort of thing. They've been designed like that. Also, hardware systems are timed. What I mean by that is that any more complex design would basically run based on a synchronizing clock. So everything is clocked, it's timed. Things happen at very well-defined periods of time as the clock dictates. Sometimes we can have multiple clocks, but generally devices tend to be synchronous in nature, so there is a synchronizing clock there to make sure everything works properly. Because of all these things, traditional software is not really sufficient for this type of task. You need really a dedicated hardware description language for it. A language like C wouldn't be able to cope with this sort of thing. While that can be useful to program more sequential devices like processors and such, that is completely inappropriate for things like FPGAs, for example, or CPLDs, so complex programmable logic devices. In terms of the design flow, what we have here is a kind of A to Z, really, as far as a hardware description language is concerned. They can take us pretty much from the process of converting the original idea, which could be in quite high-level terms, up to sometimes even fabricating an integrated circuit, a chip. The whole process will include a sequence of steps depending on what we are trying to design, and that is the so-called design flow. And of course, to follow this design flow, we are basically making use of electronic design automation tools, or CAD tools, or ECAD tools. Different names for roughly the same thing, really. And hardware description languages are essentially one of these CAD tools, or ECAD tools, if you wish. Why do we need it? Again, because current systems on one hand are very complex, and on the second hand, particularly when dealing with very complex devices, being able to decompose them and operate at different abstraction layers to manage that complexity would be extremely useful. Generally, that design flow contains a number of tools, and the job of those tools is essentially to automate the whole process of moving from one abstraction level to another, and to help us improve basically productivity and use different tools for different steps as required. So that's basically the idea behind why we need things like this. Generally, depending at which step we're talking about and which part of the design flow we're referring at, you might have different names for some of those steps. Sometimes we deal with editors, which essentially allow us to input some VHDL code, for example, either as text or perhaps some graphical form of entry, like a schematic maybe. We have simulators, which would essentially, once we wrote the software, allow us to test that software by providing some inputs and generating the outputs for us. And then it is for us to decide if those outputs are correct and behave exactly as intended. Sometimes we use analyzers, and those tend to happen or to be part, if you wish, of the various stages of the process. And the job of those analyzers tends to be to check for correctness and compliance to the rules at every stage of the process. And then finally, and this is typical for hardware description languages, we have synthesis. And this is basically the process of transforming, say, from VHDL code into the programming file that we need to then burn into an FPGA or CPLD to configure that device to perform that particular digital functionality that we are targeting. You could see all those in slightly more graphical terms if you look at this flow diagram that we have here and some of the tools that might be used at the various stages. Here, basically, you have an example of a set or a flow which takes us from the specifications, from the idea, straight to fabrication. Now, for this module, we're not really interested in the last two parts of this process, the physical design and fabrication, because we're not really manufacturing integrated circuits or designing integrated circuits. We're really just programming existing programmable logic devices like CPLDs and FPGAs, so complex programmable logic devices. And you can see how different type of tools could be used at different parts of the process and roughly what sort of things they relate to in terms of the specifications there. We'll go through a bit more detail to see what the various stages of the process are in a second. But generally, if we were to show all the typical design steps that we must go through in order to put our idea into practice and then basically end up with a chip or perhaps a programming file if we don't pursue a physical domain design. First, we start with the idea, the specifications. We then create the logical design, and then we verify it, we simulate it. If the simulation basically indicates that we have some potential issues, we need to go back to the logical design creation, fix those errors, simulate again, and we keep doing that until we're satisfied that it works as intended. Once that is done, we can proceed then to generate the later stages of the process. So essentially doing the typical physical and manufacturing processes if we are dealing with the later stages of the process and targeting a chip. Okay, so what next? In terms of forms of design entry for hardware description languages, what we need to do is, on one hand, we could resort to using graphical design forms, and those could basically be either things like schematic editors, or indeed that could happen at block level, where we have larger blocks which we try to just connect together in a schematic-like fashion. So on one hand, using graphical tools could be closer to hardware, but that's not typically how we tend to use it. On the other hand, it might be just joining together larger designs. And then the most common form of entry is basically text entry. So here I'm talking about VHDL language, for example, if we refer to our VHDL language, where we use the VHDL language to create our design. Okay, so as I said, VHDL is one hardware description language. Verilog is another well-used hardware description language, but generally speaking, Verilog doesn't really have as high of a market share as VHDL, so VHDL is more popular. Verilog tends to be perhaps a bit more popular overall in the United States and parts of Asia, but in terms of the overall market share across the world, VHDL basically has the largest market share. Okay, so graphical editors. What are we looking at here? Sometimes, depending on which particular levels we are targeting, this might well be taking the form of silicon level editors, and that's where we are trying to design physical chips. Generally speaking, that's not something we are going to look at. I'm just mentioning it for completeness. In our case, again, we don't really want to design integrated circuits, create new chips. We are just trying to program programmable logic device chips, which exist already. So in our case, the more relevant form of a graphical editor would be schematic editors. So this would be essentially relying or looking quite closely to what you would have in terms of a typical schematic that, for example, you use in a CAD tool like OrCAD or Altium or similar. The whole process is essentially all about schematic capture. It's about capturing the schematic of the device. Generally speaking, that could be a fairly tedious process. So this tends not to be quite as efficient as programming in VHDL. Generally speaking, programming in VHDL would tend to be quicker at doing this sort of thing. But sometimes mixing and matching can be very useful. And we will be covering this sort of example in practical sessions as well, just to see how the Xilinx software, for example, allows us to mix schematic with VHDL as well, which is quite handy. In terms of the schematic editors, which for us, of course, are the more interesting part of a graphical editor, this is all about using existing libraries to put some graphical components on our worksheet and then to interconnect those components with wires or buses. Essentially, what we do end up with would be a structural representation. So the structure of that schematic, which would be called a netlist, and that netlist will tell us how the various components used are interconnected to each other, which pin connects to what, how they connect to various ports, and all that sort of thing. What is also useful in Xilinx is that all those components that we put on a worksheet come with a library that can be used for simulation. So basically, once we have the schematic on the worksheet, we can also perform a simulation for it using a test bench. A test bench is basically the way Xilinx can provide the inputs for a design in order to simulate it. These libraries tend to be very extensive, And basically, they would contain pretty much all the devices that various manufacturers have. So Xilinx, if you're looking at what programmable logic devices they are manufacturing, you would find a huge list. All those are available as libraries in the Xilinx software, and they can be basically then used for designing either using a hardware description language or a schematic editor or both. Some of these library components can be generic, which would allow very easy retargeting, but some of them tend to be specific, so they are tied to a specific part number. So, for example, a Spartan 3 FPGA or a simpler CPLD. Each chip might have different pinouts, different complexity. All those libraries exist in there. In terms of the graphical user interface side of things, things are very simple, really, and they are pretty much what by now you should be fairly familiar with. You start with an empty worksheet, start a new project, say. You select from a library all the components that you need to put on that worksheet. You label them, you put some ports, and then you use the mouse to wire them accordingly. And that way, basically, you create a schematic. So I'm talking about something like this, for example, where some of the library parts that we are using are AND2 gates and OR3 gates. So essentially, we're using a OR3 gate, which is a 3-input OR gate, a generic one in this instance, and AND2, which is essentially a 2-input AND gate. And then we are using wires to connect all those outputs from the AND gate to the inputs of the OR gate. Then we are using some input and output ports, the X's and the Z. We place some labels in there to identify which particular gate we are targeting, and generally those wires would also have some names, which generally tend to be hidden, but we can also put additional labels on them if we want to. So something which is fairly similar to what happens in other CAD tools. And most of the design tools that target programmable logic devices allow this type of entry as well, and Xilinx allows them as well. The primary form of entry, though, is really the text-based form of entry, where essentially we can choose a specific language like VHDL or Verilog, and other tools might support other languages as well. So when you create a new project, you select what your language is going to be, and the Xilinx ISE allows basically to select both VHDL or Verilog, one of the two. Of course, in our case, we'll be using VHDL. And then basically you just use the type editor with syntax highlighting to type the design in. If you really want to, you can even use external editors, which might have some syntax highlighting, like Notepad++ in Windows or VI Emacs in Linux. But of course, you'll be best to always resort to using the internal built-in editor rather than an external one. So essentially, a package like Xilinx ISE contains everything we need to in one place, so we don't really need to use any sort of other external stuff there. Once we type the VHDL instructions there, that would be checked for errors, and that would be part of the compilation stage of the design. And if there are any errors, those would be highlighted so we can fix them. Once the errors are fixed, we can basically proceed to the next step of the process, which typically would be to perform a simulation. For that to happen, we need to select a test bench, which would be essentially to provide some inputs that we want to use for simulation purposes. And then once you press simulate, the tool basically will generate the output that corresponds to those inputs. It's not going to tell us that it works correctly or not. It's our job basically to look at those output waveforms and see if they work properly and they match what we would expect for those kind of inputs. If that's fine, then we proceed to the final step, which would be to synthesize the design. And that will create ultimately a programming file that we can just upload into a complex programmable logic device like a CPLD or FPGA, and that will program that chip to perform that particular digital functionality. So there you go. That's kind of the typical workflow that we tend to employ in connection to the various forms of entry for this type of hardware description language. Now, earlier on, I said that when it comes to the various levels of abstraction that we can use, we can operate at different abstraction levels. What does that mean? The three key practical abstraction levels are the structural domain, which is very much similar to or akin to performing things in a more schematic way, where essentially we have some primitive components or subblocks, which then would be interconnected together to other subblocks to form a larger component or a larger design. And then we have perhaps one of the most common types of abstraction layers, and that would be the behavioral domain. As the name suggests, this is basically meant to be more high level, and essentially it will describe things using the high level side of VHDL to pretty much describe the behavior of the hardware that we are trying to design. So how the output needs to respond to the various forms of input. This could work for smaller components or could work equally well for very large designs as well. And then finally, the last fairly common domain is the physical domain. This is only meant for designing integrated circuits and is not something we're interested in. I'm just mentioning it here for completeness. So generally, as far as our VHDL designs will be concerned, we'll be operating either in the structural domain or in the behavioral domain. So we'll be employing those two strategies really. Mostly behavioral, but structural is possible as well. Now, at this point, some of these things might look a bit abstract. So let's try to link them all together. What does behavioral domain means? What does the structural domain means? How do they tie up to each other? And how do they all link with the physical domain? The Y chart is very good for that. And as you can see in the Y chart, we have essentially a behavioral domain branch, a structural domain branch, and then we have the physical domain. So let's see how all those things kind of map to each other. And here it is. So if we start with the highest possible level, we start with a system. Now, if we want to design a complex system, that might well contain a number of components, and that takes us to the structural domain, where basically there might be processors and all sorts of other high-level stuff. Okay, those processors, if we go back using that arrow to the behavioral domain, will run some sort of algorithm, because that's the job of a processor. Those algorithms, if we ping back to the structural domain, those essentially will rely on some components inside of the processor. For example, the arithmetic and logic unit, the RAM, and so on. But those arithmetic and logic units or the RAM or any other resource inside of the processor, at the end of the day, are all about register transfers, transferring data from one register to another and processing it one way or another in between. Register transfers, to refer back to the structural domain, rely on things like gates, flip-flops, etc. to store that data, because basically a collection of flip-flops forms a register and you can store data inside of it. Of course, gates, flip-flops, etc. at the end of the day perform some logic transfer functions of some kind, and those logic transfer functions at the end of the day relate ultimately to some transistors if we were to look at the inner part of the hardware. Transistors, of course, and now we are moving to the physical domain, are all about, okay, so what is the layout of the transistor, what's the layout of the cell, module, floor plans, and then finally physical partitions. So that's all about the design process of a chip. So that's basically how the various things relate to each other in a fairly top-down level, and how the behavioral domain is closely linked with the structural domain as well. Again, the physical domain we're not really interested in as part of this module, so really our focus will only be and always be on either behavioral or structural or both. Okay. So let's look at this in a bit more detail and have some examples just to wrap our head around it. So here are some of the typical abstraction levels. The lowest one is the silicon level, so we're talking about chip design in that respect. Then we have the circuit, gate, register, chip, and system. And those match quite nicely with that specific branch of the Y chart that we've seen already. So how does a design look for those particular abstraction levels? And let's start with the lowest one, the silicon level. This is how at the silicon level things might look. This is all about the so-called stick diagrams. So if you're familiar with chip design, this is basically how ultimately the diagram of a chip looks like. You have different either metal layers, silicon layers, in order to create different transistors and so on. This is an example of a inverting gate created using MOS technology. So what we have here, it's a PMOS transistor on top, and on the bottom we have an NMOS transistor with the gates connected to the input A, and then the metal layer that connects to B would be the output of the system. So to create an inverting gate, a MOS inverting gate in this instance, that's how you would do it if you look under a microscope at a chip which implements that functionality. So this is the so-called stick diagram. Again, we're not really interested in all that. This is just an example to give you an idea what an input or an output at the silicon level might look like. If we go one step higher and we're looking at the circuit level, the same component that we've seen previously at the silicon level is now shown here at the circuit level. And basically we have our PMOS transistor and NMOS transistors connected in the way we've just seen to create this inverting gate. So that's basically an example of a circuit level, in this instance showing the circuit using transistors. If we're interested in going one step above and looking at gate level, gates typically are made of a number of transistors and perform specific functionality. And here we've got two examples. We have a set reset flip-flop, which at the bottom of the slide is shown as a generic symbol. And at the top, it's shown in terms of its inner implementation. So you can implement basically a set reset flip-flop using two NAND gate if you connect them in the way it is shown up there. So this is an example of a gate level design. If we move one step higher, that takes us basically to the register level. Here we have a number of registers, the ones denoted by reg. Each has some clock, there is some hardware in between, and there is basically a register flow there. Data goes out and into these registers as required by whatever circuit we are targeting. So this is a typical example of a register level. If we move one step above that, we then reach the chip level. Here we might have different chips performing different functionality. So we can have a microprocessor here, a RAM chip, a chip which performs parallel port functionality, a USART chip, and so on. And then those are connected together using wires and buses as required. So this is basically one higher up compared to the previous level of abstraction. And if we go even higher, then we finally reach the top of this structure, and that would be the system level. And here we can have basically different subsystems connected to each other. So we can have a computer connected with a USB TV card connected to some data acquisition hardware and some control mechanism. And all those are then connected using some relevant buses or ports. So you get the idea. As we basically move higher up in that pyramid, things become basically more abstract, more further away, if you wish, from the nitty-gritty of transistors and gates and all that. And basically designing with hardware description languages can work either on a bottom-up approach or top-down. So we can start our description very high at system level and go down as required, or indeed we can start somewhere lower up and then build things up towards the system level. Hardware description languages have been basically designed with exactly that sort of thing in mind. And you can also see here the typical design track that we tend to follow. So generally, where we're operating at system, chip, or register level, that tends to be behavioral domain related. While when we operate at gate, circuit, or layout for physical domain, that tends to be more closely related to structural designs. Sometimes it's not quite that clear cut, but that's generally how things kind of relate to describing based on behavior versus describing based on structure. So as far as we are concerned, if we're looking at the Y chart, we're only really interested in the two ovals that we have there, the algorithmic and system design chunk and the structural and logic design chunk. Those relate basically both with behavioral and structural. We're not really interested in the last two of them, which relate to the physical domain, because again, we're not really targeting chip design, we're just programming existing chips. And this all tie up quite nicely with how these forms of, or how these levels of abstraction relate to the various forms of entry that various tools can provide. And in here, basically, we can represent them in multiple ways. We can represent them as text, as discussed, as pictures, as state tables sometimes, as timing diagrams, or perhaps as schematic. And again, just to show you some examples, here is basically a design type of entry, which is using pictures, so a fairly graphical way of data entry. This would be how a finite state machine can be designed. And you can see the state diagram on the right-hand side, and that basically has the state names inside the circles, and then the various transitions and outputs laid out in order to move through this finite state machine. So that could be one form of entry, and Xilinx does have support for this type of entry for finite state machines in particular. As a timing diagram, very often we tend to use graphical test benches, which is why we are still using version 10 of Xilinx, to provide exactly this, to provide the inputs to our designs to allow us to basically simulate it and provide the outputs. So that would be something that we'll be doing quite a bit throughout our practical sessions. Some tools, Xilinx doesn't, but others might well be, could provide inputs as a form of state table. That could be another possible way. Other tools could basically provide inputs as a circuit, and Xilinx does have this form of entry as well. So schematic entry, in that case, you place some symbols on the worksheet and you connect them together, and then you connect them to some ports. And again, as I said, through our practical sessions, we'll be playing with the various forms of entry for Xilinx ISE as well. And then finally, in terms of text entry, this is basically the VHDL programming language in our case, or any other hardware description language. So this is an example or a part of a VHDL program. You can see how some things in there are new things which you haven't heard about before, things like process or signal or architecture, but other things you would have seen, if, else statements, that sort of thing. Those are common in a lot of other programming languages. So, of course, all these things we'll be starting to learn from our next lecture next week. So, we have various forms of entry. We put that design entry in. Next step would be to perform simulation. That is the job of the simulator. And the Xilinx tools in our case have quite a competent simulator, which basically, with the aid of a test bench, would provide the inputs that we want to use for simulation. So what the various input values would be. And then as soon as you press simulate, it will use those inputs to generate the outputs. In Xilinx in particular, those test benches can be graphical test benches. And this is why we are using, again, version 10 rather than a newer version, because newer ones no longer have the graphical ones, and those are invaluable for our purpose. We can also use text-based test benches, which are essentially specific test benches written in VHDL, but those are a lot more complex to create. And then finally, sometimes, depending on the tool, Xilinx doesn't, but other tools might also provide some interactive user inputs as well. So as far as Xilinx is concerned, for us, we'll be using quite extensively graphical tools. And then finally, we'll also be using test benches written in VHDL later on, but it will take us a couple of weeks to finally reach that level of the language to learn how to do that. And meanwhile, we'll be using the graphical ones, which are very easy to do. And essentially, the job of a test bench is to pretty much be like something that wraps around our design. So if we have this VHDL design, which is shown in white in the middle here, that VHDL design will have some inputs and it will have one or more outputs. The job of a test bench is to kind of encapsulate the whole of the design, provide the input stimuli, and then basically generate the output results. So that's basically what a test bench does. And again, that can be done either in a graphical fashion, by just providing some input diagram with the mouse, or we can write a VHDL test bench specifically in the VHDL language, which is the more complicated one. But this is really the first key part of the process aside of learning VHDL itself. This is basically the thing which we are using to make sure to validate that our design works properly. And only when we are satisfied that the results match correctly what we would expect for those input stimuli, only then we would proceed to the final stage of the process, which would be to simulate this design, to synthesize this design and deploy it in a programmable logic device for a one-chip design solution. So folks, this is pretty much it for today's lecture. So just to quickly summarize, hopefully this gave you a good flavor of what a hardware design language it's all about and what are their typical characteristics, how they tend to be different from other programming languages. Also gave you a good flavor of how the design process it's meant to look like, what the various abstraction levels at which we can design are, and a bit of a flavor into what the various forms of inputs and outputs are, and a bit about the process that a hardware description language tool tends to follow. From text entry to graphical and schematic, to simulation and to synthesis. So that's it from me, folks, for today. Thank you very much for taking part in today's session.